about this original Stardust mission, next step was to visit Comet Bill 2. Let's see, thank you. And the idea was to fly by Comet Bill 2 and collect dust in a capsule and return that capsule with the dust to Earth for analysis. That was done successfully 2 years later. Next step, please. The capsule with the sample was returned to Earth in January 2006. And since then, these samples have been analyzed in laboratories around the world. Next step. And they continue to provide important information about how comets were formed and about the earliest processes in the solar system. So Stardust itself was a great success. And the thing to remember was that not only was it a great success, but it left a perfectly working spacecraft out in space. And so the next step shows us that in 2006, we decided to ask NASA to send this spacecraft, to reuse it, and send it on another mission of exploration. The target, the next step, please, Comet Tempel 1, that's the comet that was visited by Deep Impact in 2005. So why go back to Tempel 1? Well, there are two answers. One is that Tempel 1 turned out to be unusually interesting. The next slide shows us that in places on Tempel 1, we see layered terrains, which probably contain information about how comet nuclei were put together. And we would like to see more of these terrains. Deep Impact saw only about a third of the surface. We would like to see more. And as the next slide shows us, we would also like to see more of the areas that Deep Impact saw, these smooth flows, which apparently suggest that comet nuclei are not only modified by processes from the outside, but also by internal processes. So there are things that we would like to find out about Tempel, which we don't know at this time. But the next time step shows us probably the most important reason for going back to Tempel 1, and that is that this will be an opportunity for the first time to see how much a comet changes between two close passages to the sun. Deep Impact saw the comet in 2005. We'll be seeing it one comet year later, just after its closest passage to the sun in 2011. So the question is, we know that comets lose material, but the question is, how much does the surface change and where does the surface change? So we'll be able to answer that question by comparing our images with those taken by Deep Impact in 2005. So to achieve these two objectives, we have a definite plan. It's summarized in the next time step, which shows us a surface map of Tempel 1. The gray mosaic shows us data that were obtained by Deep Impact in 2005. The yellow area, yellowish area, is the projected new coverage on Valentine's Day. As you can see, there is a region of overlap where we can be looking for changes, and there is a region where we're looking at new territory that was not seen by Deep Impact to extend our knowledge of the comet. Now, you also notice that there is a bullseye in the middle of this diagram, and that is the location where Deep Impact in 2005 excavated a crater. The next time step reminds us that that impact threw up so much ejecta that Deep Impact never saw the crater, so it could never complete the experiment of seeing how big the crater is and what that tells us about the mechanical properties of the comet surface. That's important if we're ever going to go back to a comet, land a spacecraft on the surface, dig up material from the surface to bring it back to the Earth. We need to know something about mechanical properties. So here, we have a chance to complete the Deep Impact experiment. So to achieve all of these things, as will be described in a few minutes, we have chosen an encounter time where we can do these two things that we want to do. And we have chosen a mist distance of 120 miles from the surface of the comet. Shown in the next time step are some of the images that we expect to take right at closest approach. Not only will we be taking 72 high-resolution images, we'll also be collecting information on the amount and the type of dust that surrounds the comet. And these measurements will be described in a little bit more detail by later speakers. Let me just say that the resolution that we expect to achieve about 12 meters per pixel at best, is sufficient to address all of the objectives that I've discussed. In the last time step, I just want to remind us that we are getting closer and closer to the comet every day. The spacecraft is working wonderfully well. The spacecraft team is working hard preparing all the data-taking sequences that we'll be using on Valentine's Day. The navigation team is working very hard to make sure that we get to where we need to be on Valentine's Day. And all I can say about the science team is that the science team is awfully excited and just cannot wait to see the pictures and the dust data that we expect on Valentine's Day. And with that, I'd like to turn it over to our project manager, Tim Larson, who will give us a few more details about the mission itself.
Thank you, Joe. We've mentioned already that Stardust Next is a bonus mission, and it takes advantage of some key factors. One, we have a spacecraft that's still working well after being in space for almost 12 years now since launch. It's traveled almost 6 billion kilometers since launch, so it's got some mileage on it, but it's still working well, able to do another mission. We also have a scientifically desirable target, or an interesting target that we can get close to with the fuel that we have left. And most importantly, we have a team of people that has the skills and innovation and the dedication needed to pull out this kind of a mission. We have people that have been flying the spacecraft at Lockheed Martin in Denver, Colorado, since the time it was launched. So some wonderful, dedicated people that know the spacecraft inside and out, know how to make it do what we need it to do, and that's what really enables this mission. As you may recall, this is the second comet encounter for NASA in the last 4 months. The Deep Impact spacecraft flew by Comet Hartley 2 in this last November. That was a great success. But like comets are all different, also comet missions and flybys are all very different and have their own unique sets of challenges. So let's talk about our spacecraft first for a little bit and some of the features of the spacecraft and some of the challenges that we're dealing with here. You'll see a scale model here of the Stardust spacecraft. You see at the top of the spacecraft are the solar arrays that generate the electric power that we use to power the spacecraft and to operate all the equipment on board. Also on the top, you will see this larger antenna. That's our high-gain antenna, part of our radio system that we use to communicate with Earth, and that's what enables us to get the higher data rates to be able to get all this data back down to Earth. And then you'll see these bumpers at the very front here and in the front of the spacecraft body itself. These are the shields. This spacecraft was originally designed as a comet flyby spacecraft, and these shields were designed and put in place to protect the spacecraft as it flew through the coma of the comet and to protect it from dust particles impacting the spacecraft. At that time, at 6 kilometers per second, this current next flyby will be at a speed of a little over 10 kilometers per second. And so these shields are what provide our main protection for the spacecraft. Now, in terms of instruments that will be gathering data as we fly by the comet, if you look at this side of the spacecraft, you'll see this feature right here. That is the navigation camera with its mirrors and periscope that is able to look out past the shields as we approach the comet. And then on the other side of the spacecraft, you'll see another instrument that comes down with a sensor sticking down below. Again, that's another sensor that's out in the flow of the dust. This is the Comet and Interstellar Dust Analyzer instrument that will help us characterize the dust environment that we fly through. And then the third instrument is mounted right in the circle that you see at the front of the spacecraft, and that's the dust flux monitor that will further help us characterize the dust field that we fly through. So these are some of the key features of the spacecraft that has done so well for us over the years. As mentioned earlier, this spacecraft is repurposed. We've recycled it, and it's had a whole entire life. And I'd like to show you with the first animation that you'll see here. It'll show you a little synopsis of the life of this spacecraft, starting with the launch in 1999, February of 1999. So this spacecraft is coming up on 12 years in space. It's had a long and illustrious life, well beyond its original planned design life, but it's still working well. Since its launch, it traveled halfway out to Jupiter and back. It executed a flyby of asteroid Anne Frank, and it also executed then the flyby of Comet Vil 2. After that flyby, where it collected the dust samples, it returned that capsule back to Earth, creating a large fireball as it came through the atmosphere. It was the fastest man-made object to re-enter the Earth's atmosphere, and it's the first time that we've been able to return samples from outer space back to Earth. After that flyby, the spacecraft continued, circling the Sun, and now we've been able to retarget it to meet up with Comet Tempel 1. And after all of that, it still has some fuel in the tank. But that's one of the challenges that we're working with here, is the remaining fuel and managing the remaining fuel. With the way we design our spacecraft and our missions, we account for all kinds of uncertainties and unknowns, and that's why we usually have some fuel left after our primary missions, and that's what enables these kinds of extended missions. However, the challenge is to make sure that that fuel lasts as long as you need it to. Everything we do on the spacecraft consumes fuel. It is a spacecraft that's controlled strictly by reaction control thrusters, and so every time we turn the spacecraft, every time we point the spacecraft, our daily just dead banding as we control the attitude of the spacecraft, all of that consumes fuel, and so we have to predict all of that into the future, predict everything we're planning on doing with the spacecraft, calculating how much fuel that's going to consume, and making sure that we have enough and we control our activities to make sure we have enough fuel to make it through the flyby and playing all those images back to Earth. So that's been one of our biggest challenges, and it's one that we pay very close attention to, and I'm happy to tell you that we really are confident in having enough fuel to finish up this mission. Although after this mission, there won't be much left that this spacecraft can do. In the process of retargeting the spacecraft and taking it over to Comet Tempel 1, we conducted 3 additional orbits around the Sun. We conducted 5 targeting maneuvers, and the largest one of those maneuvers was one that we executed last February. Now that maneuver was a special maneuver for us because a year before getting to our target, we had to decide when we wanted to arrive at the target within the matter of several hours. And that was our best opportunity to change that arrival time. If we had waited until we have seen the comet, or as we get close to the comet, say for example now, we would have very little adjustability left. We'd maybe be able to adjust our arrival time by maybe an hour at most. So we had the ability, if we did the burn a year before getting to the target, was one of our best lever, times we had the best lever arm in our trajectory to be able to adjust our arrival time. That's when we had our best shot at doing that. So we had to make our best predictions, and Steve's going to talk to you a little bit about that process of predicting what phase of the comet we expect to see when we get there. And based on those predicts, is how we chose our arrival time burn. This was a 23-minute burn of our rocket engines, and it delayed our arrival at the comet by about 8 or 8.5 hours. And so that was a major event for us almost a year ago, last February. So now as we get closer to the comet, we'll start getting busier and busier. A lot of the activities that take place can only take place once we get very close and have the knowledge that we need to be able to design these appropriately. So our last targeting maneuver, as we approach the comet, is 2 days out. That is the last maneuver that will be fully designed to target to our 200-kilometer flyby distance, and that will be executed 2 days before we arrive at the comet. Right after that maneuver, we'll be taking our last optical navigation images, and those are the images that we'll use to build our best prediction of our actual flyby point and the path of the trajectory of the comet relative to the spacecraft. Once we build that, then we will load up at 24 hours out. We'll load up our final sequences that have been built with that latest estimate of the time of closest approach. And that final data on the comet trajectory will also be loaded onto the spacecraft. And from then on, the spacecraft will be working autonomously. We cannot control the spacecraft real time. And here's another challenge with this mission. The spacecraft is currently basically opposite the sun from the Earth. So we're about 2 astronomical units away from Earth at the time of encounter. That means when we send a comet up to or command up to the spacecraft and wait for the confirmation that command arrived there and was executed properly, that round-trip light time is approximately 40 minutes. So there's nothing we can do to command the spacecraft or control it real time during a flyby like this. Therefore, everything has to be programmed ahead of time, put on board the spacecraft and sequenced, and everything happens autonomously on board the spacecraft. So 1 hour before we get to the comet, the spacecraft will turn to orient itself with these shields facing forward to protect itself as it flies through the coma of the comet. About 30 minutes before closest approach, our AutoNav software will activate, and that's essentially an autopilot software on board the spacecraft that analyzes the pictures that we're taking of the comet, figures out where the brightest spot is, calculates that as being the center of the nucleus, and then adjusts the position of the camera mirror so that we can keep the nucleus in the field of view of the camera all the way through the flyby of the comet. Then if you'll roll the second animation, this will show you what we expect to see as we fly by the comet and the kind of images we expect to get of the comet as we fly by if everything goes as planned. This is assuming a 200-kilometer flyby about 20 degrees south of the sun line, and if the phase of the comet is as we predicted. And so it's exciting to see this kind of information coming out and see these kind of simulations that show us what we expect to see on February 14th as we fly by. As we fly by, our closest approach will be about 8:30 in the evening Pacific time on Valentine's Day, February 14th. In the few minutes around closest approach, we'll be taking the bulk of our images. We'll be taking 72 high-resolution images. We cannot transmit those to the ground real time because of the flyby geometry, so we have to store all of those on board in the spacecraft memory. An hour after the flyby, we turn the spacecraft to point the high-gain antenna back at the Earth, and at that point we'll start relaying all this information back to Earth, and that'll take approximately 12 hours to get all this data back down on the ground. Our first images should be hitting the ground around midnight Pacific time on the evening of the 14th. So that's what to expect during our flyby and some of the key things that will be happening. And to talk to us a little bit more about what we might see when we get there and the geology of the comet, I'd like to introduce Pete Schultz.
Thanks, Tim. Deep Impact was really a groundbreaking mission with many firsts. Groundbreaking also by the impact probe that actually produced a brand new impact on the nucleus. So the first time we're going to be going back and we'll actually get to see what's happened since the time we were there. Now, the Earth has been around the